Hello YouTube! Yet again it's time for another review, and this time we're going to have a look at this STM32F4-DISCOVERY kit from ST. This kit contains the new STM32F4 series, which is a Cortex-M4 CPU ARM microprocessor, and this inexpensive kit contains this new CPU and a lot of different peripherals. So we are going to have a look at this kit, the different functions, and how it can be used. So let's open it up. Inside the box we'll of course find the board itself, but we will also find a small inlet, a leaflet, sorry. This leaflet contains some short information about the board itself. We have some useful things to know, and on the back we have a getting started guide. Other than that, it refers to the homepage, the ST homepage, to get started using the kit. The board itself is a small little form factor. You can see this is my hand. But it contains a lot of different peripherals and stuff, great stuff. In the center of the board we have the CPU itself. This CPU is the STM32F4, the 407 VG. This means it's a 100 pin CPU, but it contains 1 megabyte of flash and a total of 192 kilobytes of RAM. So this is a very large chip in the series. 1 megabyte of flash is a very large number and very large amount of flash. So you can make very large applications and also use it for storage for example data or images, if you're going to connect it up to a display. The other things this board contains on the top is the ST-Link. The ST-Link is the onboard debugger. You can also buy an external ST-Link, USB ST-Link, but this one already has the ST-Link embedded on the board. This ST-Link enables you to program and debug the chip itself using a numerous of different applications, such as ST's own environment. But later on I'll get back to that and how to use the ST-Link. The great thing about the ST-Link is also that you can actually disconnect the ST-Link from this chip and then use the external SWD connector for programming other devices, or even programming your new project where you've been using an STM device. Okay, so let's continue to have a look at the board and see what else it contains. At the bottom we notice two connectors. We have a USB, this is a USB micro A or B, and a audio phone jack connector. These two things are connected to the processor. The USB micro connector here is connected directly, as this STM4 series contains USB on the go capability. So if you want to use either you want to use this on the go, which can be either USB host or USB client, it requires you to buy a cable or a adapter. This adapter for the USB host should be a USB micro A or B to a USB B female, and opposite if you want to use it as a client. The audio jack here is connected to the onboard audio DAC IC. This audio DAC IC is connected to the processor, so you can play audio with a decent in decent quality because of this DAC. The chip itself also contains a number of output DACs, which you could of course also connect to some audio output and use them by that. Okay, great. Another thing the board also contains is actually a microphone. This is a small embedded microphone embedded in a chip. And this is the STMP32F4-DISCOVERY microphone chip. And this is connected to the processor by a digital bus. And ST has also provided us with a number of libraries and example codes to see how this can be used. The last thing the board also contains, which is a great thing, is actually an accelerometer. In the middle here we have a so-called MEMS chip. And this is the STLIS302DL, which is a 3-axis accelerometer. And this specific kind of chip is actually used in other applications too. For example, quadcopters and balancing robots, to enable them to measure the gravity, the gravitational force. So because this is embedded on here, we can of course read the orientation of the board or read the acceleration if we want to. Around the chip we have 4 LEDs. These 4 LEDs are 4 different colors, and each of them are connected to an individual pin on the IC. So you can use them for debugging purpose, or, as I'll show you later in the example, they are used to show the acceleration read from the accelerometer. Yeah, so we also got a button and two buttons. One of them is reset and another one is a push button, single push button connected to a pin, so that can be used. And of course you probably have also noticed all the pins out here. These pins are connected directly to the microprocessor. Some of them are used by some of the peripherals, the onboard peripherals, but you can of course use them anyways. You just have to take care of how you use them, and if it's, for example, the I2C bus which is connected to the accelerometer, you'd have to take care of that, and that this accelerometer is connected to the bus too. On the back we have the pins too, a bit longer, so this can be used if you are going to make your own board, expansion board, or just going to connect it and wire it up to your own projects. Now you might ask, why should we go for this new STM32F4 series instead of, yeah, all the 3 other series, the F1, F2 and actually also the F3. The F1, I've been using that for quite a while and I'm very happy for the STM32 series. I really love their products and the series in total. They got a very good resource database and good documentation. So of course I would try out this new chip, but what is actually the difference? Well, this new chip is, instead of being Cortex-M3 as the other series, this is an Cortex-M4. Of course this is an ARM, which is the Cortex series, it's ARM processors, but this new M4 speeds up the processor and adds some other commands, some assembler, internal commands to the command set, the thumb instruction set. As this new series, the Cortex-M4 also includes a floating point unit. This is a great device to add to this processor, because a floating point unit enables you to do floating point math a lot faster. This means an increase of over 10 times for the speed of doing floating point math operations on a standard Cortex-M3 without a floating point unit, and on this Cortex-M4 with a floating point unit. I'll make some tests later on to show you the increase in time, or the decrease in time for doing these calculations. The other thing to notice is that this processor is capable of running at 168 MHz, while the STM32F4 is only capable of running at 72 MHz. So that's also a quite amount of increase in the speed. It's actually over 100% increase. So on this board we only have an 8 MHz crystal, but the processor itself is capable of doing a PLL, and the PLL this frequency up to 168 MHz, which runs very, very neat at this speed. The other thing to notice on this board is of course the flash size. You would be able to get flash sizes on the other devices, but it really expands the number of possibilities with this board. And this board, this STM32F4 board, is actually priced at only around $20. So this is a very, very inexpensive board for only around $20. So you get all these devices, the processor itself, and also a onboard debugger and programmer. You don't have to invest and buy any other tools or stuff to get it working. You get this board and a lot of different peripherals, and also the opportunity to connect it to your own stuff, to your own projects, and use it in there. So this board is very, very inexpensive development board from ST, which enables you to use their processor in your own project for good. So I definitely think that the idea of creating this board at that price range was to get some of the hobbyists, which before were using the Arduino and the Embed, for example. Probably compared to the Embed, because the Embed is an ARM processor. It's the LPC from NXP. This board adds some better functionalities and higher speeds than the Embed itself. So hopefully, I think that ST hopes to be able to sell some of these boards to the hobbyists.
Now let's have a look at the different compiler options available on the market to use with the STM32F4 series. The first option I'm going to talk about is the one recommended by ST, which is also used on the examples, because ST provided examples for this compiler and this IDE, and it's the Atomic True Studio. Before, the Atomic True Studio had a version called Atomic True Studio Lite, STM32 Lite, which were great in the way that it hadn't any code limitations. The only limitations were the debugging, because you were only able to debug with one breakpoint at a time. So there were no code limitations nor any time limitations, which made it great because you could use it for your projects and use all 1 megabyte of flash that's on the Discovery board. The breakpoint limitations were okay. You could just remove the breakpoint and add it somewhere else, and it worked without any problems. The difference were that you could only use this Lite version, at all, with STM32 devices. Now Atomic True Studio decided to combine their STM32 Lite version, or STM32 version, with their ARM version, which supports many different other devices, ARM devices from other manufacturers. The problem with that were that they decided to change the Lite version. So the Lite version is now code limited to 32 kilobytes of flash. There's no debugging limitations, but now it is code limited, and that makes the problem, because now we're not able to make our large projects anymore. But yet again, this Atomic True Studio is a bit expensive. Sorry. But you can get their light version, which can compile to 32 kilobytes of flash. You can also decide to try out their 30 days pro trial evaluation, as they call it, which gives you a full version with no limitations at all for 30 days. The Atollic True Studio relies on the GNU GCC open source compiler, which is always expanding on the device list, and it also relies on the an Eclipse-based IDE, which is their IDE, and the things you pay for is the register, device register informations and readings, and especially also the project generator. And then you also get some other middleware and RTOS, as you'll see here. Another option would be the Crossworks for ARM, the Rowley Crossworks for ARM. The Crossworks for ARM is not that expensive. The other version, this Atollic, costs around 4,000. This, for the hobbyist, can be bought for a personal license at $150. And this Crossworks for ARM is a great tool and comes with a great IDE. I haven't actually been using this myself, but I've read a number of posts, a number of threads that this is a good tool, and it supports some different debugger and programmers too. The Atollic True Studio supports the ST-Link, which is also why ST recommends them, and I'm not sure if this is supported in the Crossworks. But the compiling environment is great, and their compiler is great, especially because it's also priced at that range for personal use. Another option is the Resonance Right7 IDE and the ARM ARM. The Right7 IDE were free a while ago, a while back. I don't know if you remember, but I've been using the Right7 a lot before. I've been using that because I bought their debugger and programming JTAG debugger and programming adapter for a less expensive price. And the only limitations were 32 kilobytes in debugging. I were able to make as large projects as I would like, but it was limited to 32 kilobytes of debugging. That was great, and this Right7 IDE also relied on the GNU GCC compiler, which is free, but then it adds the debugging and the register readings, etc., etc., and it was for free. But now Resonance decided to sell this, not the IDE, but the compiling toolset. What they did, I actually don't know, but they decided to sell. Here is the light version, which supports some Cortex-M3s and ARM9 and ARM7 devices for around €100. This includes a 1-year support contract, and here is where you should be aware when buying compilers that the support contract means how long time you're going to be able to get support from them, both in the way of you contacting them because you have a problem, but also in the way that getting product updates for the compiler, IDE, etc., fixing bugs and such. So after a year, you'll not be able to get product updates anymore without buying an extended support contract. You will of course be able to use the previous version, the most recent version before your support contract expired, for as long as you would like, but you will not be able to get the product updates if a new device is added, etc. Now for some of the more expensive versions, more commercial used versions, we have the IAR Embedded Workbench. The IAR Embedded Workbench, also known as IAR EW-ARM, is a very powerful compiler and IDE. It's easy to use and supports a great amount of devices. It's commonly seen in use in commercial applications because it's very expensive. We're talking over we are talking many thousands of dollars for a commercial available license. They support, as I said, different devices, and one of them is of course the STM32 devices. All of the devices F1, F2, F3 and F4 of course. But in our use, this is very expensive, so I don't think you probably are going to go for this IAR. But the great thing is that they actually provide a free evaluation version, 2 free evaluation versions. They provide a time limited one, which is limited for 30 days, just as the Crossworks version. But they also provide a size limited version, which is limited to 32 kilobytes of flash. And that is great because you can use this great tool as long as you can keep your projects under 32 kilobytes of flash. So if you would like to go for the more professional ones, you should decide whether you are ready to pay for those, pay the large price, or you can keep your projects under 32 kilobytes of flash. Another more expensive option, which is also very common seen, is the MKK Arm. The difference on IAR and MKK Arm is not big. It's 2 competitors, but when you buy development boards, you will actually most of the times notice that it comes with both examples for IAR and the MKK Arm toolset. The difference is that they are both C compilers, but the syntax is of course the same because it's C, but the integration and the initialization routines, etc. is a bit different. Also the linking process, and that's why the examples has to be a bit different. But yet again, the MKK Arm is also very commonly seen, and it's a great tool. If I could say my opinion, I like the MKK Arm best. The MKK Arm is also very expensive. I think I saw the price for around $10,000 US. But then it also comes with many different libraries, peripherals, middleware libraries as they are called. And those are the one you see here on the screen. For example, file systems for SD cards, USB, flash, etc. And then it also comes with USB host, USB device support, TCP/IP, etc. Again, MKK Arm comes in different versions, which supports more or less all the same devices, but it comes with different limitations. Either in the professional, we of course have all the features and also all the middleware libraries, whereas standard doesn't have the middleware libraries like the USB host device, etc. Then they also have this light version, which is not time limited in any way, but it is debugging limited to 32 kilobytes, and also flash generation, the linking limitation of 32 kilobytes. So if again you can keep your projects under 32 kilobytes of flash, then you're good to go with this light version. The great thing about both IAR and MKK Arm is the IDEs. The IDE for the MKK Arm is the U-Vision, the so-called U-Vision, and it integrates nicely with many different debuggers and programmer adapters. Carl have of course made their own, the so-called U-Link, but you can also use the ST-Link if you'd like. It supports that as great as the U-Link. So if you're ready to pay a lot of money for a compiler, I think you should decide whether to use IAR or Carl. Those are great compilers, but very expensive. Then, if you could keep your projects under 32 kilobytes, yeah, you should have a go with them. Try it. So, a free alternative to all these more or less expensive compilers are the so-called KukocQID. I just stumbled upon this a couple of weeks ago, and I actually find it very good, reliable, and useful. The KukocQID relies on the GNU GCC open source compiler, as both the Atomic and resonance does too. And then it also builds uses an Eclipse-based IDE, which integrates nicely with the different programming adapters, like the ST-Link or another FTDI device or J-Link. The problem might be the supported list of devices, as it builds upon this GNU GCC, which supports almost every ARM devices available. But the problem is that they limit the devices because they also have this project generation feature. So like the Atomic True Studio, this KukocQID can also generate the required project files. But in this way they also limit the amount of devices because they would like to be able to generate these project files. So if we go to NXP, we'll see this is the processor used on the Mbed, for example. It is of course supported. But now if you go to the ST tab, we'll see that actually only the F1 series is supported, and then the F4 series. The F2 and the F3 series are not supported yet, and I'm actually amused to see this F4 because when reading up on this before, I could actually not find this F4 on the list, so I've been able to find a beta version of the KukocQID. But now it seems that they updated the list just as I'm speaking, so that's great. Then they have also updated this to version 1.4.1, which supports the F4 series of devices and also supports the project generation for those, so that's great. I've tried this KukocQID and I find it very useful, and it works great, integrates with the ST-Link very nicely, and you're able to debug and program as much as you would like. Yeah, I would say if you were going for a inexpensive free alternative, I would choose the KukocQID and have a go with that. But for this video I'm going back to the Atomic True Studio, as I've still got my light version, not code size limited light version, installed on my computer. And as I said, the examples provided by ST comes with examples in this Atomic True Studio version, so that's easy for me to show you how the different examples works. Here I got it running. It's as you can see, STM32 Lite version. So let's have a look at the different examples provided by ST and have a look at them in action on the board.
To connect the board to the computer, you are going to need a USB cable. For the debugging purpose, we're going to use a USB-B Mini, as it's called. So you'll require a USB cable with that in the end. I got one here with for the computer and for the board. And if you would like to test the on-the-go support of the STM32F4 device, you're also going to need cables for this. And as I said, these are micro A or micro B cables. For the host purpose, you should get a USB micro A or B to female B to be able to connect it to, for example, a USB memory stick or a hard disk or some kind of other HID device, Bluetooth dongle. And this plugs directly into this on-the-go port, like that. Sorry, I should have to turn it. There. And then you'll be able to connect your USB memory stick in here. If you would like instead to use the on-the-go port as USB client, you should get yourself a USB client cable with a micro in the end, the USB micro A or B, and a normal PC USB A connector in the other end. And then again, you could just plug it in and use it as a client. But now let's have a look at the first example, the example that actually comes with the board when you powers it up, when you have received it. It's an example that shows the accelerometer and also the client functionality of the on-the-go port. So let's connect it up to the computer.
When you first plug it into your computer, you will notice the LED starts blinking, and on the computer the device will be recognized as an ST-Link. Currently you won't see it on my computer as the driver is already installed, but you might require to install a driver, and this driver can be found on the ST download page listed on the package. When installed, you should actually be able, in my case in Atollic True Studio, you should be able to debug and program the device with other examples. But now first let's have a look on this example. The initial example just blinks these LEDs in a circle. These are the 4 LEDs I've been talking about, connected each to an individual pin. And if you press the button, which is also connected to an I/O, it will go into the accelerometer mode. In this mode, the LEDs would be used to show the acceleration, the gravity. So if I tilt the board this way, you'd notice that the top LED begins to blink faster and faster as I tilt the board. Now you can't even see it blinks. And if I go back, see it blink slower and slower and slower. And here it's stable. Also, if I move to the other side, where can you see there? And you can see the different orientational LEDs. So this is actually just an accelerometer demonstration. And if I press the LED, the button again, it will go back to the LED blinking routine. But now let's have a look at what happens when we connect the on-the-go port connector to our computer for the client purpose. So now I'm going to take my USB A to USB A micro and connect that here to the on-the-go port on the bottom. Green light will indicate that power has been connected. And now, if we press the button again, it will actually also enumerate as an HID device on our computer. So when I move the board, you'll also see that the mouse begins to move. So now it's initialized as a USB mouse. I can move up, down, or sideways only. Yeah, you can have much fun with this. To use it as a USB mouse. So this shows the USB on the go client side device functionality of this ARM processor, this new STM32F4. So let's unplug this so it doesn't do weird things with our computer. And then let's have a look at the compiler itself, the Atollic True Studio IDE. The Atollic True Studio here, I don't know if you're going to use this, but I'll use it in my example. We have opened this, the example you just seen, which we have downloaded from the standard firmware pack, which is available on the ST site. In here we got a list of different files, the different libraries. These are the required libraries for standard functionality. For example, the standard peripheral drivers are the common drivers used for the different peripherals on the board. And then we got a specific library for the board here, which contains the different libraries for the accelerometer, audio DAC, etc, etc. Then we also got the on-the-go driver and the USB device library. All these are provided by ST and works with the GNU GCC, but it also works with or you can also find versions for Kyle or IAR. Now let's open the main.c file, which is the main project file, the main code file. In here we'll find the main routine, which is run at the initialization, at the startup, And if we go to the bottom, we will find the demo exec, which is the demo we see on the board. In here, you'll notice this is the STM libraries coming in: STM evil, LED init, and LED off, and LED 4, 3, 5, 6. Those are the LEDs on the board, which is named after those. Which is named after these. So you'll be able just to turn them on and off by running these commands, as long as you have remembered to include this discovery library. Waiting for the user button to be pressed. When it's not pressed, it just toggles these LEDs as we saw in the video demonstration. And when we press this button, we wait before it is released, and then it goes into this accelerometer mode. It initializes the accelerometer, blah blah blah, etc., and also initializes the USB if possible, and then it goes into this interrupt routine where it outputs the states of the accelerometer to the LEDs, and this routine can be found down here at the bottom. Not here, sorry. This is the timer for the PVMs. You notice the LEDs, but it can be found in the interrupt in here, where we receive the data. Here we have the SysTick handler, which is run at a frequency set in the beginning. Here we have a frequency of run every 10 milliseconds. That means a frequency of 100 Hertz. We run the SysTick handler, and if we're in the condition of getting the accelerometer, the demo enter condition equals 1, we run this below here, where we get the accelerometer and turn it to the LEDs. These are the capture compare registers, which is used to set the PVMs of the different outputs. The great thing about the STM32 series is also the great number of timers, hardware timers. So you can use dedicated timers for PVM, and a lot of different IOs supports these because they are attached to some of the timers. Now let's load up one of the other applications, one of the demonstration applications. So I'll go and import one of them from this standard firmware discovery firmware example zip file. This time I think we are going to select the audio playback and record feature. This project uses both the audio DAC for audio output, and it also uses the microphone IC chip for input. It actually also uses the USB on the go device for USB host functionality for saving the recorded WAV file. So let's open up the project. As we see, this project actually consists of two sub-projects. The media in flash is just a simple audio playback example, where audio is saved into the flash from programming. So this is already pre-made audio that is saved into the flash. As it's 1 megabyte, there's more than enough for just playing short audio clips. While the USB key uses the record functionality to record a WAV file to a USB memory stick and then play it back afterwards. So first, let's have a look at this media in flash. We're going to open the main file, and I'll go walk through that, but let's first build it and check if it's okay. It says nothing to build for media, so it's okay. And in here we have a main where it sets up the board, and this is not defined because we are not using the media. We'll use that in a moment. So instead it just starts to play back through the audio DAC through I2S, the I2S port. And this is all done in an interrupt-based environment, where we have the wave player here, which in this wave playback loop goes into and checks if something has happened. We are going to play through flash, where the audio is saved, And then it's also using the accelerometer for sensing whether to start or stop, because this LIS accelerometer from ST has a register that supports to be set up for clicks. It is interrupt based, so when you touch the board as a click, it will send an interrupt, and this will either start or stop the playback. In this mode, and in the other USB key, it will either change the mode from recording to playback or from playback to recording. So that is what happens here. It checks if we are playing or not. We should resume or we should stop the player if in repeat state, and currently the repeat state is set to 0. So we are just repeating the audio playback. And that's actually this for this demonstration. So let's test that by pressing the little bug up here, which will start the debug. It will transfer the compiled file to the board. You'll see that the debugger starts blinking, and you'll notice the LED stop blinking from the other example, as it's now programming the so-called elf.elf file into the board. And this might sometimes take a while. And this is because the audio file is pretty large. To have a look in the meanwhile at that audio file, we have this audio sample. You are opening a large file. Yes, we are, because here we have the audio sample, which is just the sampled values of the output that should be sent to the DAC. This audio sample is I don't know how large this is, but you can see that it's 45,000 lines, and each of these are 16-bit integers. So there's a lot of flash. The flash has been used a lot here to save this audio sample. So we'll just keep waiting. And now it has successfully programmed the ELF file to the board, to the processor, and we notice that the layout changed to debugging, and we'll see that the pointer here, the cursor, stays at the first line in the main. So now let's take a speaker. In this case, I got this. This is a paddy wipe, as it's called. This is a small speaker that uses vibrations and uses the table or something else, the surface, as the speaker. So let's just use that as the speaker. So I'll connect the jack to the jack connector, like that, and let's start the playback. On the computer, we click the play,
and we'll hear the sound. I don't know if you can hear it. I'll just take this so you can hear it. And if I now tap the table, it will stop, because it senses that the accelerometer senses the click, and if I tap again, it will resume the playback. I could also use the button. Just like that. Okay, so that's the in-flash example. Now let's have a look at the other USB memory stick example.
Back at the computer, we have now ended the debugging session, and we are going to select this new Media USB Key project. Here we click Build Project to confirm that it has been built, and it says nothing to build for USB key. Then we are going to debug this, so we are going to click right click at it and say Debug as Embedded C application. Then it will program the application to the board, and this will not take that long because it doesn't contain the audio file as before. And then we're going to take a USB memory stick and plug it into the board. So to plug it in, we see that it has finished programming. So before starting it, I'll just plug this USB memory stick in. So we take our USB micro to USB host, USB female A connector, plug in the memory stick into this end, and plug in the other micro end into the USB on the go connector. When this has been done, we are going back to our computer and we will start the debugging session by pressing the play button. And now we'll see that it has turned green, and now it is actually recording. So when we press the blue button, it will stop and start playback. And nothing happens. Sorry, there it was. And we'll start playback, and we can go back to record. Now it is recording, so let's hear what it sounds like. Now recording, so let's hear what it sounds like.
I don't know if...
Now recording, so let's hear what it sounds like.
Can you hear it?
Now recording, so let's hear what it sounds like. Now recording,
and this is saved on the USB memory stick through USB on the go. And again, it is also using the tab.
Now recording, so let's hear.
And if we press the button, we go back to recording.
We go back to recording. We go back to recording.
Yeah, and okay, it misses something there, but then let's see. But no problem. Yeah, right.
Yeah, right.
Yeah, well.
Yeah, right. It works. And it actually works pretty well. So this is an example of how to use the USB on the go for USB host functionality. Yeah, actually I think that's it for this review. I've went through some of the examples. Another great example provided too that I'll not show is the firmware update capability, that you can actually install a bootloader onto this. So this bootloader lays in the lower part of the flash, and then like DFU, when you are going to update the firmware, you just put the binary firmware file onto a USB memory stick, and then you plug it in, and then it will update at startup. So that's it for this review. I hope you learned something new, and that you'll buy this board and make something great with it. I'll be using this board in my next quadcopter project, which some of you might have been reading a bit about. So I'll keep you updated with new projects with this board. Thank you for watching.